Welcome.
Thank you very much. Thank you very much for having me. Can everybody hear me? Okay. Today I would like to talk about cultural macroevolution, and specifically the big question that I want to try to answer, if tentatively, is why large-scale complex societies have arisen in the last 10,000 years in human history. So let me start by, first of all, explaining what I mean by cultural macroevolution. The distinction between microevolution and macroevolution is made in biological evolution. So in biological evolution, microevolution is the change in gene frequencies within populations, whereas macroevolution is long-term, large-scale changes at the level of whole species and and other types. So in cultural macroevolution, we can make a similar distinction. The microevolution is then the change in the frequency of cultural variance within a specific population. In fact, this has been proposed as a definition by Cavalry, and Feldman, and followed by Boyd and Richardson and other luminaries in cultural evolution field. But I would restrict this definition only to microevolution. So macroevolution there is large-scale changes in cultural traits of all groups, including what people loosely call societies, but as you will see, I will make a more specific definition. I will be talking about political organizations or polities. So I'm interested in large-scale and long-term changes of cultural traits of polities. And there has been already several individuals who have been using this definition in their work. Now, let's talk just one comment about the micro to macro connection. In biological evolution, the reigning dogma is that the characteristics at the macro level reduce, can be completely explained by microevolution. But in cultural evolution, this is clearly different. Because, well, some group level traits can reduce directly to individual traits. So, for example, if you want to know what is the average life expectancy in a particular society, in a particular polity, then this is the aggregate of survivals of all the individuals that live within that polity. But other traits don't reduce to individuals. So one example is institutions. I will be talking a lot about governance institutions. Clearly, I cannot say that I have this institution or that institution. Institutions are characteristics of all polities, and therefore, when we want to understand why such polity characteristics have changed with time, we need to do the analysis at the level of polities. And of course, characteristics of individuals have an effect. So whether individuals hold, internalize democratic norms or autocratic norms will have an effect on the governance institutions at the polity level, but still, again, the evolution and evolutionary dynamics of such polity level characteristics cannot be reduced directly to the characteristics of individuals. All right, so this slide illustrates the big question that I want to address in my talk today. If we look at the evolutionary history of our species, roughly speaking, 200,000 years ago, plus minus, is when most authorities date Homo sapiens. We lived for 95% of our evolutionary time. We lived in small-scale societies which can be called foraging bands, consisting of a few dozens of individuals and perhaps being part of a somewhat larger ethno-linguistic group of a few hundred, of some hundreds and maybe a few thousand individuals. So the social scale at which people interacted and cooperated was much smaller than today. Today, most of the population lives in states, and there are many large nation states counting tens and hundreds of millions of individuals, and even in two cases, more than 1 billion individuals. And this slide illustrates the timing when the first polities have arisen. So we know that first centralized societies that we could call simple chiefdoms arose roughly 7,500 years ago in Mesopotamia. They were replaced by complex chiefdoms. Archaic states appeared about 5,000 years ago, and so on and so forth. So what I would like to emphasize with this slide is that the social scale over the past 10,000 years has changed dramatically. I would even say astronomically, by 6 or 7 orders of magnitude. This is a huge transformation, which is what I would refer to as the great Holocene transformation of human social life. At the same time that social scale has changed, the institutions governing our societies have also changed, as indicated by me using such terms as chiefdoms, states, empires, and so on and so forth. So to me, this is the most basic fact of social evolution, of human social evolution. This dramatic transformation that happened very rapidly in evolutionary timescales. So how and why did this happen? What are the evolutionary mechanisms explaining this great Holocene transformation? That's what I will try to answer in my talk. So there are many theories, and I'm not going to spend a lot of time talking about them, but let me give you a very rough classification of them. First of all, pretty much all authorities agree that agriculture, productive way of economy, is a necessary condition for truly large-scale, complex societies. Very few people would argue against that. But once we have admitted this as an explanation, we come immediately to the conclusion that agriculture may be necessary, but it's not a sufficient condition, because many societies acquired agriculture for thousands of years, but never evolved into states and empires. One primary example would be New Guinea, highland New Guinea. And there is a variety of theories that can be roughly divided into two camps. Functionalist theories assume that large-scale complex societies have evolved to fulfill a certain function. So examples include develop and maintain infrastructure, management, economic management, managing scalar stress, that is organizing and coordinating large-scale societies, and so on and so forth. So these are, so to speak, nice theories. Somewhat opposing them are conflict theories, and conflict theories also come in two different flavors. First flavor focuses on internal conflict within societies. So the most famous are, of course, the Marxian and Engelsian theories emphasizing class struggle. Other theories, such as James Scott's and some other people, also point to internal conflict, and they suggest that grains make states, because grains, unlike tubers, for example, are much easier to be taxed by the elites. All right, the second flavor of conflict theories is external conflict, which emphasizes the conflict between societies. Some theories are called as known as conquest theory of the rise of state. Other theories also invoke warfare and so on and so forth. In addition to that, there are many other theories, so religious theories, probably more functionalist, but they involve some other elements. I will return to the big guns hypothesis at the end of my talk. And then there is a theory which arises from cultural evolution. This is called cultural multi-level selection theory. I'll talk a little bit about that also later in my talk. All right, so the point that I'm making is that there are many theories, but and the theories seem to be multiplied rather than being rejected. So in science, after all, we are interested not only in proposing new hypotheses, but we need to test those hypotheses empirically so we can reject some in favor of others. So the goal of the Seshat project, which again, I may just briefly mention it now, but I'll talk more about the details later, is to actually generate the needed database, the empirical base that we need to test those different theories against each other and to make progress. So it's a systematic program of testing hypotheses that I and my colleagues embarked upon, roughly speaking, 12 years ago. Okay, so now let's jump into this. Before I talk about the database, about Seshat, let me introduce you the conceptual framework, the quantitative and modeling conceptual framework that I will use to make sense of the variety of theories and also to represent the process of cultural macroevolution. And here I use a very well-known mathematical framework of nonlinear difference equations in the form that's depicted on this slide. And we can use all the discrete time difference equations are closely connected with continuous time differential equations. One can actually go back and forth, but because our data comes in discrete form, I find it more natural to use this difference equations system. So what do we have here? First of all, we have on the left-hand side, we have X, Y, and so on. These are the state variables that evolve and that we want to understand. So they reflect cultural characteristics of the polity. And here is a formal definition of the polity. So polity is an independent political unit, a political organization that has sovereignty in a sense. And it can range in scale from independent farming village through simple complex chiefdoms, states, and empires. So, so that is the human groups that I will be focusing on, and X, Y, and Z refer to the characteristics of such units. All right, so these variables can be part of the variables that are interconnected through dynamical feedbacks. So that's why you see that X is and Y and Z are not on the left-hand side, but they're also on the right-hand side. So, for example, let's look at the first equation. So X at time t plus 1 is a function, first of all, of X of t. Because we are dealing here with evolution. Evolution is an inertial process. Basically, knowing where we were at one time step ago, actually tells us, gives us a lot of information where we will be today. In addition to X, you have other variables, Y, Z, and so on. So these are parts of the feedback loop. So you can see that X, Y, and Z depend on each other. So potentially they can all influence each other in a variety of ways. But other variables are U and V here. They are exogenous factors. So these variables are, they don't depend on X, Y, and Z. They come from outside. So they can be modeled, oftentimes they're modeled as stochastically varying variables, but we also can use them to implement step-like changes in the environment, both physical and social environment. All right. And finally, F, G, and H are functions specifying how variables interact with each other. So this is a very general framework which allows us to include pretty much nearly all the theories that people have proposed for the evolution of complex societies. This nonlinear dynamics framework is particularly suitable for investigating evolutionary questions because it captures descent with modification. So descent here is conditioning xt plus 1 on xt, all right? So that says that there is some inheritance. Characteristics are inherited. But they're not inherited precisely because there are other factors that affect them. That would be stochastic factors, or they could be factors that modify our variable of interest, such as y and z, and so on and so forth. From the mathematical point of view, the model is essentially a biased random walk in discrete time. Continuous time analogs have been used in biological evolution. They include Ornstein-Uhlenbeck processes and its generalizations. But again, I prefer to stick to discrete time because it gives us a more direct connection to data, as we shall see. And the dynamical behaviors of this model can be pretty much anything. It could be a neutral drift, so which means that expectation of xt plus 1 is the same as expectation of xt. So there's random walk essentially around that. It could be directional selection when other factors push x in one particular direction. It could be stabilizing selection when there is a particular level of x and other factors push it towards that equilibrium. And there could be more esoteric behaviors such as cycles, chaos, multiple equilibria, and so on and so forth. But I will be sticking to simpler types of dynamics in my talk today, in my analysis. All right, so it's easy enough to translate this dynamical framework into an inverse model. So now let's suppose we have data and we want to understand what these functions f, g, and h are, and which of the variables should go in. So which of the variables y, z, and so on are causal factors. They are factors that affect the evolution of x, and so on and so forth. And so what we do typically, because we now analyze the data, instead of pointing the model in the future, right, I now look to the past. So now y sub it is an observation or at time t in a particular location I, and it depends on the potential autoregressive lags. So tau here could take 1, 2, and so on and so forth. Also, we include possibility of spatial autocorrelations here. So this is the next term. Here, y at jt minus 1 is basically it's the observations of y at other locations. And a negative exponent here is a function which weights the importance of those observations as a potential impact. All right, this term, the next one, is doing very similar thing, but now we're looking at the cultural similarity proxied by linguistic distance. And then we get to the xk. These are the potential driving factors. These are the substantive variables proposed by different theories. And finally, there is a and there is a stochastic term. Epsilon is the error term. All right, so this is one particular specification of the model. I want to emphasize that this is mostly a linear model, but we can investigate nonlinearities by introducing square terms, interaction terms, and so on and so forth. All right, we can do a variety of investigations using about the specific distributions of errors and so on and so forth. So this is just one realization of a variety of models that one could use. So essentially, what I'm doing here is I am approximating F, G, and H using the Taylor series expansion, all right, using the polynomials to investigate potential non-linearities. Okay, so time lag here corresponds to 1 century. Why? Because that's how we collected data in Seshat. The data in Seshat are resolved at 1 century intervals. Okay, and the basic approach here is pretty brute force. I feed a whole bunch of different regressions, tens of thousands, and maybe even hundreds of thousands, and I sort them out by archaic information criterion, which allows us, which penalizes models for excessive number of parameters. And okay, and then once we have found what models seem to be best, we can use non-parametric bootstrap to approximate the uncertainty estimates around the parameters. Okay. All right. So without going into all these great technical details, let's step back and understand what does this formalism allows us to do. It basically allows us to investigate a variety of evolutionary causal scenarios that can give rise to correlations between variables X and Y. So typically we know, if we collected data on a bunch of qualities, I'll show you in a minute, and we see that X and Y might have a positive correlation, for example. The next question is, we realize that correlation is not causation. So how do we determine which of the possible causal scenarios holds? And we can distinguish 4 possible causal scenarios. The first one is that X affects Y, but there is no feedback from Y to X. So that would be direct causation. The other possibility, the causation goes in the opposite direction. So Y affects X, but not vice versa. Or it would be mutual causation. So X could affect Y and Y could affect X. Now notice that if we don't have time, then we would not be able to distinguish between those scenarios. And that's why I have put subscripts here, because you can see that XT affects YT plus 1 and YT affects XT plus 1. So we are here, we are in this framework here. All right, and that's quite possible because it's quite possible that X and Y co-evolve in mutual causation. Increases in X help Y and increases in Y help X. So without time-resolved nature of data, we will not be able to distinguish such scenarios. And just for those of you who are statistically minded, essentially, I'm using time lags to break endogeneity here. That's what I'm doing. Now, obviously, time lags. Okay, so another way to think about it in more intuitive terms is that when we are trying to get at causes and effects, we know that causes should precede effects. So if we find that for example, changes in Y precede changes in X, and the first scenario is not really, cannot really hold, because it contradicts the idea that causes precede effects. However, this time-resolved nature of data, unfortunately, does not allow us to perfectly get at causality because just because one change precedes another is consistent with both the mutual causation and also no direct effects. All right. So if, for example, both X and Y are driven by Z, all right, then we could see arbitrary lags between changes in X and Y. So this is the famous example of the rooster crowing. Rooster crowing does not cause the sun to rise. Okay, that's because rooster crowing and sunrise are driven by other variables here. All right, so basically what this framework allows us to do is to not necessarily resolve completely, but at least approach the causality. It allows us to test different theories. All right, but we need time-resolved data. So let me now spend just a few minutes talking about the Seshat project. Seshat, which is depicted here, is or was an Egyptian deity of scribing information and by implication databases. And the goal of our project was from the beginning to build a web of facts about past societies, both historically known and archaeologically known, or both historically and archaeologically known. And this web of facts is connected along spatial, temporal, and conceptual dimensions. So temporal dimension is critical because we need time series. We need to see, in order to understand and test hypotheses about evolution, we need to observe change with time. And that's why temporal dimension is very important. Spatial is also important because influences between societies can spread through space. And conceptual dimension refers here to how different variables might be affected. For example, I'll show you in a minute correlations between a matter of governance institutions and social scale. All right, so we're interested both in surveying the diversity in social evolution trajectories and to identify general patterns. So our diversity is equally important as generalities. And the main goal, but not the only one, is to test and reject theories about social evolution. So the way it works is that first we have to sample the space, because right now it's not possible yet to get all the data known to historians and archaeologists into a database. So to start, we need to sample. And we came up with a sampling scheme where we divided the world into 10 regions, such as North America, South America, Africa, Europe, Southeast Asia, Oceania, and so on and so forth. And within each of them, we selected 3 locations. One of them where centralized societies were fairly ancient, like this one here is Oaxaca in Mexico. Then another one where they were pretty late, Iroquois area, and one where it was intermediate. So in this case, it's Cavalry. Right, I will do this for all of the different regions. So we had initial sample of 30, but since then it has been expanded. I'll show you in a minute. So what we do that, this is just remember, it's a sampling scheme. These locations are not units. The units are the polities that occupy them. So for example, if you look at Upper Egypt here, we go back to the beginnings of agriculture. So the first Neolithic period is the Badarian here. And then we basically look at all polities that occupy this particular spot between the Neolithic revolution, whenever that happened in a particular region, and Industrial Revolution. So the last polity here is the Ottoman Empire, which of course had the capital located elsewhere, but it also governed Egypt. All right. So basically, we construct a time series by looking at which polities occupied different spots. So this frequency diagram tells us that the sample is somewhat weighted towards the present, but we do have a variety, several different locations where you go back 5,000 or more years ago. So even though our sampling intensity declines as we go back into the past, we still have an informative sample that allows us to do statistical applications. All right, so since then we continue adding things. So this red things are new, additional NGAs. Now we have more in Africa, by the way, but they have not yet been completely checked. So this is an ongoing process. All right, so let's talk about now, what does it mean? So remember that the unit is a polity. So we want to capture such things as characteristics of a polity. So some characteristics are easy to conceptualize. For example, the social scale of a polity can be captured by the estimated population of people governed by this polity. It could also be captured alternatively or in addition by the territory, if we are talking about territorial polities, and some other variables, such as number of hierarchical levels in administration, military, and so on and so forth. But how do we capture institutions? This is more difficult. So the scheme we came up with is that we take a basic variable. So you want to quantify specialized governance institutions, and then we break it into a bunch of things that could be coded in a binary fashion. So for example, we ask, are there administrative specialists? Yes or no, bureaucrats? Are there specialists in as military officers or soldiers? Because these are not necessarily, one does not necessarily imply the other. Other religious specialists, other specialized government buildings. If we have bureaucrats, if we have administrative specialists, what are the bureaucracy characteristics? What are the characteristics of legal system? And so on and so forth. So here it's 11 different binary variables. We code them as zeros and ones, and then we aggregate them by adding them up together and dividing by 11, which scales them to be between 0 and 1. So our governance, the Seshat measure of specialized governance, is scaled to 0 and 1, with 0 corresponding to none of these traits present, and 1 corresponding to all traits present. So that's the basic approach here. And here's what the data look like. So here I plot just 10 different trajectories. These are antique societies which acquire centralized regions that acquire centralized societies early. So you can see Egypt here, China, and so on and so forth, going back from 5,000 BC to 1800 or so, right? Remember that we don't go beyond the Industrial Revolution. And what you see here is these are the trajectories scaled between 0 and 1, right? So several societies, like China, for example, maxes out at 1 quite early, by the end of the first millennium BC, all right? But what's important here is that there's quite a variety of trajectories. Some societies start on this early, like Susiana in Mesopotamia, others later. Some societies gradually increase the sophistication of governance. Others do it more abruptly, like this purple thing, Latium. All right, and finally, there is, some societies don't sustain the governance, so governance can both increase and decrease. What's important here is that we have a lot of variability, and this is actually very useful to have such variability, because the more variable are the data, the greater is the statistical power, the more informative is this this data set. All right, so that's the main thing I just wanted to say. The emphasize here, don't look at all the details, but just I hope you would be impressed by how much variability there is. So we have a lot to feed to the statistical analysis. So here's, for example, one look at the correlation. All right, I'm going to get to the causality in just a minute, but here let's look at how governance. So governance is plotted over Y, and one measure of social scale, which is log transformed quality population. You can see that there is definitely quite a correlation here, and also this there are two blobs, possibly with another one in between. So there could be even interesting possibilities for more punctuated type equilibrium. I'll talk about that more later. But also notice that there is a lot of data points which are not perfectly correlated. Yes, we miss the two corners, but there is no perfect correlation between social scale and governance. So they tell us different things. All right, some of the things that tell us are similar, but other things that they tell us are different. And so that's why it's useful to look at several measures of social scale and complexity. All right, so I'm going to go pretty fast through the results, because we have just published 6 months ago, we published this article in Science Advances, so you will be able to see all the details. And because time is short, I just will show you the highlights. All right. All right. So what we do is, first of all, as I mentioned, we do a whole bunch of regressions. We have 5 different classes of theories which suggest 17 specific predictors. We have 3 response variables because we want to capture different aspects of social scale and complexity. And there are a huge number of models that we can test. And this is this explanation is for the next table. All right, so here are the results. Let me explain this complex table. First of all, look at 3 columns to the right. We have scale, which is basically the first principal component of log transformed population, log transformed territory, and the log transformed population of the largest settlement. We have hierarchy, which is the average of the number of levels in the hierarchies of military, administrative, and settlement hierarchies. And we have governance, which I explained 2 or 3 slides ago. So we have 3 dependent variables, 3 responses capturing different aspects of social complexity and scale. And then we have on the road, we have 17 different predictor variables, which can be grouped in 5 different, actually 5 or 6 different theories, so which are color coded here. The green ones refer to agriculture, the blue ones refer to various variables suggested by functional theories. Orange ones is the internal conflict. These yellow ones are religion-based theories, and red ones are warfare theories. All right, so when we do this analysis, we find actually that results are quite clear. Basically, there are 2 classes of variables that seem to be important for all 3 response variables. As you can see, agriculture and military. And in between, we see notice that this minus in or plus in parentheses, it actually reflects that this a model which uses this variable was selected by AIC, archaic information criterion, but AIC seems to be a bit more permissive. So when we use a more conservative parametric bootstrap, you find that those are not significant at the conventional 0.05 level. So what we see here is that for all those variables here and there, we see, blinking in and out some of the results, but the most the simplest hypothesis is that because we do so many comparisons, right, some of these just come out by chance alone. Also notice that, for example, for big gods, the theory proposes that there is a positive effect on complexity, but we actually estimate negative effect, even though it's not terribly statistically significant. So this is a pretty strong evidence against the big gods theory. Also notice that, only one case in information systems, we see 2 out of 3 predictors included in this particular term in the model. All right, so the conclusion here is that we support agriculture as we expected, but we also have even stronger effect is the 2 warfare variables, and therefore the results seem to be very stark. So the best fitting models are similar for all 3 response variables. Agriculture, warfare are selected. We have a high out of sample prediction accuracy. I will talk about that in a moment. But a bunch of other hypotheses are not supported. So this is a pretty strong and clear result. All right, let's quickly look at agriculture and warfare. So with agriculture, we have estimated, one of the measures of agriculture is the productivity of agriculture estimated as the yield of the primary carbohydrate source in tons per hectare per year. And so I won't go into details. This was published also about a year ago. You can see basically how we get this data. This shows the evolution in 8 out of 35 areas. All right, I won't spend much more time on that. So this variable is predictive of increases in complexity and scale, which sort of was a bit of an expected result. But on the other hand, if we plot the correlations, let's say here between governance and this and productivity agriculture, it's somewhat positive, but it's really not that striking, right? And but agri is strongly selected. So even though we don't see very strong signal at the level of simultaneous correlations, there is a strong signal at the level of it helps to predict how governance evolves. All right, the second variable is the antiquity of agriculture. So this is the lag between adoption of agriculture and the appearance, in this particular case, macrostates. So macrostates are defined as states controlling population at the peak of at least 100,000 square kilometers. All right, so what we see here is that, first of all, let's look at the left-hand side. There is definitely a bunching up. There is a characteristic time of about 2,000 years, 2 millennia, quite a long time between the adoption of common agriculture and the rise of macrostates. That's one thing. That's interesting. Secondly, this graph shows it's a necessary but not sufficient condition, because there's a whole bunch of macrostates not appearing in regions that had agriculture for a long time. But nevertheless, this is why it's a big contributing factor. We can see it here. All right, the next one, let's look at the warfare. And I'll spend a bit more time because it's less obvious what we do, how do we deal with warfare. The warfare arises the warfare hypothesis actually is not a conquest hypothesis or some other. This is actually, it arises as a prediction from cultural multi-level selection theory. So cultural multi-level selection theory integrates both functional and conflict theories because it proposes that intense interpolity competition, so selection acting on polities, drives functional integration within polities, right? So it doesn't say that both functional and conflict theories are important. No, it says that they're mixed in a very specific way. And during the Holocene, the primary mode of competition between polities was warfare. So in order to test CMLS theory, we need proxies for warfare intensity. And the idea that warfare is an important factor in the rise of states is quite well known in historical sociology. So in particular, Charles Steele has quipped that war made a state and the state made war, suggesting that there is a mutual causation scenario between war making and state making. And this idea has been developed by a variety of other authors who looked at specifically the evolution of the European states, and they look to the important changes that happened during the 15th and mostly 16th century, specifically what's known as the military revolution of the 16th century, which introduced gunpowder weapons and, very importantly, ocean-going ships. All right. So the basic idea is very congruent with the cultural multi-level selection ideas, and that is that intensification of warfare caused interstate selection pressures, which evolved the new institutions on the part of the states to become more functional, more internally integrated in order to survive in that intense competition. And we see rapid cultural macroevolution in a variety of different characteristics of states. All right, but military revolutions are not limited to the most recent one. There were other military revolutions. For example, the first millennium BCE, there was an iron cavalry revolution depicted here on this Turchin relief. All right, and before that, there were other military revolutions associated with bronze weapons and armor, chariots, and many other things. So military revolutions do two things. First of all, they result from some new innovation, technological innovation. Secondly, they cause a cascade of additional innovations, technological innovations. They also intensify the competition between polities. And by doing that, using the CMLS, cultural multi-level selection theory, we expect evolution of scale and institutions. Scale because the larger polities survive military competition better. They have more taxes, more recruits for armies, and so on and so forth. Institutional is very important because you want to be efficient, and collecting taxes also integrating large-scale societies takes more work, and therefore we expect evolution of governance here. So what happened in Eurasia is that both the iron and the cavalry were invented at a very similar time and in similar geographic locations. And so as a result of that, here we see the origins of iron metallurgy and horse riding and how they spread. So basically what we see is that they acted together in revolutionizing warfare. And so what we see is that we can actually capture not only the effect of that particular revolution, but many, by looking again using the Seshat approach, where you have 6 different categories. the use of metals, projectiles, handheld weapons, and so on and so forth. All right, and then each of this is coded as a binary variable. And you can see that in the lower right corner, we see some reflection of the 16th century revolution. Also here are clearly handheld firearms, but we also see other revolutions reflected in this particular coding scheme. So there are 46 binary variables, and we can basically adding zeros and ones together, we get a measure of MILTEC. Very similar approach to what we were using for governance, although in this case we use not 11, but 46 variables. All right, so yes, I want to start wrapping up. So here, returning back to the table of 3 response variables and 17 predictors, as you remember, we found that agriculture and warfare proxied by MILTEC actually has a very strong predictive power. So here, this graph shows instantaneous correlations. You see that in the lower panels, the correlation between agri, tons of carbohydrate crop per hectare per year, and scale hierarchy or governance is not huge. It's about R squared, correlation R squared is about 0.3, 0.2. It's a bit better for correlations between MILTEC and those 3 response variables. But again, it's not huge. But when we actually use this as predictor variables, right, we find that together they predict much better the 3 different response variables than apart. So they interact clearly. And by the way, this is an estimate of true prediction because we use, it's an outsample prediction accuracy. For the details, you can check the article, but we get R squared, prediction R squares of about 0.9. And by the way, the prediction R squared could be 0 or even negative when your model does worse than the mean. So prediction R squared of 0.9 is a very high result, unexpectedly high, actually, to tell the truth. I didn't, because when you know how messy historical and archaeological data are, it is quite remarkable that we get such well-resolved predictabilities. Okay, so basically, just as a reminder, we're looking at green and red variables that together they give us this high predictability. All right, so what's the take-home message here? Basically, that here is the causal diagram. We see that military revolution, this is proxied by the spread of iron and cavalry, and warfare intensity is proxied by MILTEC. They have strong effects on social political complexity and scale. All right. By the way, there is a very strong effect of military revolution on warfare, on MILTEC, because of this cascading effect of fundamental inventions on other inventions. Right. Agricultural productivity and transition agriculture also have a strong effect. We also detect one example of mutual causality, because at least governance has a statistically significant effect on agricultural productivity and vice versa. So there seems to be a mutual causality effect here. It's not a huge effect going back, but it's there. So this is basically what our results say so far. We can also use the fitted model as a way to predict how different characteristics of societies, of polities can evolve. So here I give an example of using the model for social scale. And we are looking at, in the model, we look at the effect of introducing iron and cavalry together. And you can see the model predicts that it gives a big kick after that. This introduction, we should see the increase of rapid evolution until, again, it slows down and approaches some kind of a equilibrium as determined by other variables. And here, what the data say, the data show very similar aspect. And I'm running out of time, so I will just say that when you start delving into the specific details of specifically the Iron Cavalry revolution, you see actually that it's a result. You see a result which is similar to. Remember, I showed you the time lag between adoption of agriculture and the rise of macro states. Here, we are looking at the next level of social evolution. We are looking at very large states, mega empires of 3 billion square kilometers or more. And what we see here is that following the introduction of cavalry into these 4 different regions within Afro-Eurasia, it takes 400 to 300 years to see the rise of a new mega empire. So warfare acts faster. There's still 300 to 400 year time lag compared to 2,000 years for agriculture, but still we see gain a very, very characteristic relationship between the introduction, between the military revolution and the rise of mega empires. Okay, and as I said, gunpowder revolution, iron cavalry revolution are not the only ones. There were others, and so here we can see their effect by looking at a different proxy of scale. Here, looking at the area controlled by the 3 largest poleages, and so on and so forth. All right, so I was planning to talk a little bit about the moralizing religion, but because in the interest of time, I'll skip this. And again, this was published this summer in a special issue in Brain, Religion, and Brain Behavior. Okay, in a special issue of a journal. So you can look it up. I'll skip this. Just I want to say that in this particular case, we find that moralizing religion has no effect on sociopolitical complexity and vice versa. So this is an example of the fourth, causal scenario where the high correlation between these two things is the result of shared drivers rather than any direct causality. All right, so to finish up, so what I hope I showed you or try to persuade you is that, well, first of all, if we step back, first of all, historical data can be very informative, and it can allow, and it does allow us to test cultural evolutionary theories. It of course helps to have time-resolved data because that allows us to approach causality much better. And it is good to have a global sample because that gives us the necessary variance. We can compare different trajectories in the Americas to Eurasia and Oceania and so on and so forth to see whether we observe similar results. There are lots of challenges remain. I want to emphasize that it's a tentative conclusion in distinguishing between those theories that have strong predictive power and those that don't, all right? But it is clear that there are strong patterns and strong results. So prediction R-squares of 0.9 or so is unexpected, and it suggests that we are dealing with very strong causal processes going on. And I want to emphasize that this data is a result of collaboration by many dozens of individuals. Actually, if we include our expert historians and archaeologists who have helped us check data, we have more than 100 people involved in the Seshat project. And of course, I want to acknowledge our funders. And thank you very much for listening.
Thank you very much. And people should feel free to jump in with questions, but I will use my part of the share to pose the first question. I thought this was really interesting. I like the idea of the underlying characteristics of society explaining the shift forward. I'm wondering about, so for agriculture, one of the main measurements was how productive it is by area units, by hectare, right?
Yes.
And it seems to me, and maybe you don't have this variable, but especially in the later part of history now, for instance, better variable would be how many people you need per output. So it's not that we use our land more efficient in more modern societies, it's that we need less people to produce the same amount of food.
Yeah.
And
yeah, you're right. I mean, economists talk about different factors of production. So labor, you are focusing on labor. I focused on land. And one could also look at the effects of, typically, there's three factors that economists focus on. So, so land, labor, and capital. Right. So what I would argue is that it's possible to do to look at productivities, total factor productivities, but it's more relevant for the last couple hundred years, really.
That was what I was going to ask you. You thought that it had shifted because the agriculture looked really relevant in the beginning, this per hectare, and then it dropped out. And I wonder if that was because in the military, the invention of new weapons could be seen as how many you can kill per person.
Yeah.
And it didn't drop off. Yeah.
But it's possible to do, and it certainly is necessary to do once we go beyond industrial revolution, because productivity, labor productivity becomes a critical variable in understanding our modern societies. So I'm in agreement with you on this.
Excellent. And with that, I will leave it to...
There is a chat question. Let me, okay.